In this presentation, we'll be looking at advanced cryptography. We'll look at a few fundamental things that are important before we go on to some of the other areas. But from there, we'll look at general encryption, the usage of private keys, how we pass keys onto public keys, then how we use the private key to prove identity, then on to PKI, hashing methods, one-time passwords, MACs, some secure functions and other encryption methods. The site that we'll be using is this one here. It's a security site, and we'll be using some of the examples on the encryption page and also on the coding page. Okay, so let's look at some fundamental areas of encryption. We'll find that encryption is littered by some key people who have made some major discoveries and inventions within sound cryptography. They include Rivest, Shamir and Alderman, who came up with the public key encryption method. It was kind of based on Whitfield Diffie's work with inside key interchange. And then Ron went on to produce methods known as MD4 and MD5, and also encryption methods. Phil Zimmerman was a good example. He created a method that allowed us to be able to sign and secure email with the PGP encryption. Then Bruce Nair has produced many encryption methods, including Twofish and Blowfish. And one of the most modern and up-to-date encryption methods is AES, which is also known as Raindial after its inventors. Okay, so what is it we have really? We have Bob and Alice, and Bob and Alice want to communicate without Eve intercepting the communications and being able to listen to them or even change them. We also want a method for Bob to be able to identify himself correctly to Alice and vice versa. We want to be able to set up communication channels where we can keep it secure, and also that we can identify that the person or thing that sent the communications was actually the real person or thing. So what we have is that we now have some sort of encoder, encodes the data. And then on the other end we have some sort of decoder that allows us to get the data back again. Some of the ways that we represent our characters, our text, is with either hexadecimal or base 64. This is a good way for us to be able to represent bit streams or cipher streams. Often we have plain text, and the plain text is then converted into some ciphertext. So for example, an A is represented by this bit pattern, a B by this one, and so on. When we encrypt it, we might see this as a cipher stream. We can then either show that as hexadecimal or as base 64. With hexadecimal, what we do is we take a bit stream and then we split it up into 4 bits at a time. And then we use a hexadecimal table from 0 to 15 to be able to represent our 4 bits. So all ones is an F, 0, 1, 0, 1 is a 5, and so on. So in this case we have a 5. This is a 1, a 2, 4, 8. So I have an 8, a 4, and a 2, which gives us 14. 14 is an E. So we have an E there. Okay, so this allows us to be able to very easily convert between our bit stream and our hexadecimal stream. The other method that we have is what's called base 64, which tries to represent our bit stream in terms of standard ASCII characters. For this we take 6 bits at a time, and then we'd have a lookup table such as this. So in this case we have a 1, 2, 4, 8 and a 16. So that's 17, 25, 25 here. So 25 over here is a Z. Then over here we have a 1, a 2, a 4, 8, 16, 32. So we have a 32, a 4, 36, 37, 38, 39. So we look up 39 and we find that's a lowercase n. Okay, so in this way we can actually represent our characters. With base 64 we make sure that we have groups of 4 characters. So what we often do is we pad with equals at the end of the string. So you can often interpret or easily find out base 64 where it has equals at the end. So let's have a little look at an example of this, and we'll go to our base 64 converter. Okay, so there's A, B, C, D, and we can see here that's the bit stream here. So this is a B, C, and a D. And you can see here this is the conversion that we get when we convert the bit streams into the. If we perhaps take the example that we had here, so it's 100 10 00 110, and then we have 0111 00110, and the next one is 011 0110 0101. Okay, so we can convert from binary into our hexadecimal. There we go. There's our Z, and there's our N, and there's our J, and there's an L. Okay, it doesn't need the equals in this case because it's managed to fit the bits into the 4 characters. Okay, hexadecimal, base 64, and binary are the main methods of representing our ASCII characters. You can try this one out with some random words. You can see what it gives you. Okay, so you can see here there's some of the equals coming in, and you'll find it's always 4 multiples of 4 characters, so that's where the equals comes in. The other operator that we have with inside encryption, or the 2 main operators that we have, we need to keep things quite simple to make sure that if we know the secret, some sort of secret, it's easy for us to be able to decrypt or convert the ciphertext back into plain text. So we use very simple operators that make it easy to do that, and one of the most basic ones is exclusive OR. With exclusive OR we always end up with the same, we never lose any information when we exclusive OR something with something else. So with that we end up with the table 00 gives us 0, a 01 gives us a 1, 10 gives us a 1, and a 1 and a 1 gives us 0. That's the exclusive OR operator, a bit like a binary adder. So 1 and 1 gives us 0, 10 gives us 1, 00 gives us 0, and so on. The other operator that they have is either rotate left or rotate right. So rotate left means that the bits go that way, and then any bit that comes off the end goes back into the start. So if we rotate something, we rotate left by 2 bits, then if we rotate right by 2 bits, then we get the same thing back again. So let's have a look at the exclusive OR operator. Okay, so let's see if we can find that. Here we are. Okay, so we're taking test, and then we take the letter T. This is what we get. So this is test, T, E, S, T, and this is the character T. So when we exclusive OR that together, this is what we get. If we then exclusive OR it back again with the same key, we'll actually get back our original word, which is test. So in this case, we never actually lose anything with inside exclusive OR. Same with rotate left and rotate right. We never lose anything, any information when we code with them. So the challenge that we have is obviously to make it so difficult for a computer that if the receiver, such as Eve, does not know what the basic secret is, then it's very difficult for her to be able to determine it. So we need to make things very difficult for the computer, because the computer could try brute force with all the keys that are possible to be able to crack a code. So the main things that we do is that we either have lots of something, such as having lots of keys. The more keys that we have, the more that it will take a computer to be able to, more time it will take a computer to try all the keys. The other thing we can do is to make it so difficult that it's mathematically difficult for it to be able to crack a code. And one of the most difficult things that computers find with mathematics is to find the numbers, two prime numbers that make up a multiple. So if we took the number 5, which is a prime, and 11, take one away from each other, and we'll make that 4 and that 10, and the answer is 40. These values are quite small, so it's fairly easy to be able to, for us to be able to determine what the original numbers were to make up the prime numbers. But when the numbers are extremely large, such as this one, it can be very, very difficult to find the two factors that cause that value through multiplication. So let's have a look at some examples here. Okay, so this is just a very basic program that determines the prime numbers. So you can see that it doesn't take too long for the machine to be able to find the numbers, prime numbers between 1 and 1000, and also between 1 and 10,000. Takes a little bit longer for 1 to 100,000, but it can find them. So normally what the computer will do to be able to crack something like the calculation of two prime numbers, the multiplication of two prime numbers, is to have a table already set up. The problem though is that not all the prime numbers have actually been found, and it can take a lot of memory to actually store all the prime numbers. So let's see if we can generate two prime numbers. So there's one there, 101,999. 41 is another prime, and when we multiply together, that's what we get as the calculation. So a very simple program that really just takes some prime numbers. But let's look at what these numbers actually look like. Well, let's try a prime number. So let's try 999. Obviously that isn't a prime number. Try that, and that is a prime number. And let's look at the numbers that we actually get. So this is an example of a 512-bit number. So you can see these are very large numbers, and when multiplied together we can see this is the size of the numbers that the computers had to deal with just for 512 bits. So we've already looked at prime numbers. Another important concept is the greatest common divisor, which takes two numbers and finds out the largest, the smallest, the greatest common divisor between the two numbers. So let's have a look at this. Okay, so an example, we'll use 9 and 15. So in this case, the largest common divisor will be 3 between the two of them. Okay, so we take 21 and 14. The largest common divisor is, of course, 7. And the basic algorithm that we have is this one here. We can actually see how we actually calculate it. We keep dividing the values, find the remainder until the remainder becomes 0, and then we take the last value as the largest common divisor. You can try a few examples. So 42 and 56 should give you 14, and so on. In public key encryption, what we do is we make sure that the greatest common divisor between two numbers is actually 1. So let's look at the basic concept of encryption. What we normally have is that we have Bob and Alice who are sending messages, and then to keep the messages secret, we have some sort of key that changes the message into our ciphertext. Ciphertext is then sent, and then the same key is then used to be able to decrypt the message to give us back our plaintext. If Eve does not know the key, then it's very difficult for her to be able to read the communications or even change them. So this is known as key-based encryption. And 3 main methods that we have for encryption are symmetric encryption. We use the same key to encrypt as to decrypt. So it's a bit like a padlock. We lock the padlock with one key and then we open it with the same key. Asymmetric encryption uses 2 special keys. When these keys are generated, we can encrypt with one, and then the only key that will decrypt it is another one. So we typically call this one the private key, and this one would be the public key. So Bob would encrypt with his private key, and then send to Alice, and then Alice would decrypt with his public key. That's used in identity checking. Normally what would happen is that we would get Alice's public key. We would then encrypt with her public key, send it over, and then she would use her private key to be able to decrypt the message. As we'll find, signing with your private key is used for identity. Signing with someone else's public key is used to keep the message secure. The other methods that we have is one-way hashing, where we can go one way, but it's almost impossible to mathematically go back the other way. Methods for private key encryption is run, reverse, RC2 and RC4. We can have DES and 3DES and AES. For public key, we have RSA, DSA, LGAMO, and so on. Then for hashing, typical methods are MD5 and SHA-1. To give you some idea, about 1024 bits RSA is required for reasonable security, and that's equivalent to a 160-bit LGAMO elliptic curve key. So the strength of the key typically relates to the number of bits that are in the key. So obviously if we just have one bit, we could only have two keys, a 0 and a 1. If we have 2 bits, we can have 4 keys, 0, 0, 0, 1, 1, 0, 1, 1, and so on. So it's 2 to the power of the number of bits gives us the number of keys. The more keys there are, the more difficult it gets to crack it. So 64 bits, we can have 1.84 times 10 to the 19 different keys. And we can see that here. Okay, so here is the number of keys, and here we are for 64. That's the number of keys that are possible for 64 bits. The two main ways that we create the cipher is either with a block code, where we take one block of the message block at a time. If any of the blocks aren't quite full up, then we pad them with a certain character. Then we take each of these blocks and we'll add the encryption key, and then we create a cipher block. We then put them all together, and that becomes the transmitted cipher block. The other method we can use is with a stream code. With this we take our key, such as with RC4. We then create our initial seed, typically called an initialization vector, and then that will create an infinite key. The infinite key is then exclusive ORed 1 bit at a time with the plain text stream to give us our output. So you can see here a 1 and a 1, 1 and a 0 gives us 1, a 0 has been resulting from a 1 and a 1, and so on. So what are some of the key private key methods that we have? Okay, so private key uses the same key to encrypt as to decrypt. The problem that we have in the methods that we've actually seen, that it might be possible to actually play back a piece of ciphertext. So in this case, if we've encrypted something and we want to play that back, we could copy that and play it back to Alice, and it will look like a correctly ciphered text. So what we often do is we often add a little bit of salt to the encryption process so that the same message doesn't produce the same output. Okay, so this is what we have with the electronic codebook. With the electronic codebook, we take a block at a time and then we encrypt. Each block is encrypted with the same key. So if it was the same block, then it will always come out as the same encrypted block. This can be a major problem as we might say the word hello, and we can see here that hello is always ciphered as that. An intruder could find out that that message maps to that. The intruder could say send a message in saying hello, how are you, and then the person could reply back with a message that they probably can guess what the text is, and then from that they can actually map the cipher to the plain text and then copy and paste between the ciphers. What we normally do though is that we add some sort of initialization vector to make sure that the cipher that we produce always changes, and that is adding a bit of salt. The IV vector can then change between each of the ciphers, such as we could add 1 onto each initialization vector, or we could make it random. The cipher block chaining method, or CBC, actually works by taking our initialization vector and then exclusive ORing it, or using it as part of the encryption to be able to create our cipher block. Then the output from one block is then fed into the next block, which will then obviously change it if it's the same. So you can see here that this is AES with the electronic codebook, and even though it's high quality encryption, we can still see that the same blocks are still encrypted in the same way. When we use CBC, we can see here it's completely random. To give you an example of what code actually looks like, this is an example of DES. We take our 64 bits, then we do an initial permutation. So for this, bit 58 goes first, and then bit 50 followed by bit 42. It then goes through 16 different iterations, and there's some sort of permutation of the key that's actually added into each of the iterations. So it goes through each of these stages, and then there's an inverse that happens on the very last permutation. With DES, we have a 64-bit key, but only 56 bits are actually used in terms of the encryption, because 8 of the bits are actually parity bits. So this considerably weakens the key. Okay, so this is what happens in each of the basic stages that with inside DES. This is our inputs here that go in, and we have some sort of permutation that go on, and it gives us our resultant. And here we have what's called an S box, or a substitution box, and that's what we have here. It just scrambles the input and the output. So the main private keys that we have DES, which is 56 bits. DES is seen to be insecure because it uses such few bits. So we now use 3DES. With 3DES, we take a key, we then encrypt with that key. So we take our message, and then we encrypt, and then we decrypt that with a second key, and then we re-encrypt it with the first key. So the strength of the key is really the two keys together, 256 bits. So 3DES is secure up to about 112 bits. RC2 is another popular one, a 64-bit block code, but the most popular now is AES or Raindam. So let's have a look at these codes. Okay, so here's DES. So we can take a message. We'll apply our key. We can see this gives us our base 64 and our hexadecimal, and then hopefully we should end up with the same result. 3DES. Need a longer key. And hopefully when we decrypt we'll end up with the same message again. And we'll try AES. Okay. And what we'll see is that we've selected a static IV value here of 0 to F to give us our 16 characters for our IV in this case, and obviously if it was a real code, we'd make sure that we change that over the messages. So now we'll have a look at Blowfish with CBC. Okay, so first we'll look at Blowfish without CBC. and we'll see the problem that we have. So let's put in Fred and a key of Bert. And when we generate the code, every time we generate the code, we get the same cipher, which means that someone could actually take our cipher and determine what actually was the plaintext associated with it. So in this way they could actually copy and paste bits of the cipher. For example, they could take this message and another one and paste them together. So let's have a look at CBC. So with CBC we have an initialization vector. Okay, so let's go for Fred and Bert, and we have an initialization vector of 1. And here is our output. Okay, there's our base64 and our hex, and this is the decrypted value, just to make sure that it works. Now we try a value of 2, and we see that the encrypted value actually differs. Okay, so obviously what's happening there is that we're taking an initialization vector and then we're feeding it into the first block conversion, and then that's getting chained on to the other ones. In this way that we always change the cipher that we actually have. The initialization vector is typically incremented each time we send a new message. Okay, so we've seen how Bob and Alice can use the same secret key to be able to pass encrypted content. So we can use AES, blowfish, twofish, des, 3des, and so on. But the problem that we have is that how does Bob pass the key to Alice? And how does he make sure that Eve doesn't actually know what the key is and isn't listening to the communication? And this is the general problem of being able to pass keys between Bob and Alice. So those keys might relate to a session key. So every time that we connect, that Bob and Alice connects, then we can generate a new key, or it could be a long-term key. So the problem that we have is how does Bob send Alice the key so that we can use a private key or symmetric key encryption system. And that was solved by Whitfield Diffie, who came up with the Diffie-Hellman algorithm, and it's one of the most widely used in terms of passing keys. What happens is that we generate random number on either side. Then we do a calculation. Bob sends Alice something. Alice sends Bob something. And even though Eve listens to it, she cannot determine the end key that's actually created. In this way, we can create session keys, such as if we connect over a VPN connection, we could generate a new key every single time that we actually created a session. Okay, so this is the basic algorithm. We agree on G and an N value. Bob generates an X value. Alice generates a Y value. Then Bob makes a calculation. G to the power of X is random value. Then modulus N. And then on the other side, Alice does G to the power of her value, and it takes mod N. Then these are sent over the line on the other side, and the value that's received is then used on the other side, and at the end of it, K1 and K2 should have the same value. So let's look at a simple example. Okay, so we'll do a very simple one here. Okay, so let's calculate a G and an N value. So now we'll generate an X and a Y value. So then Bob has taken 7 Alice 16. So then G, which is this value, is then taken to the power of 7, and then we find the remainder when we divide it by n. So this is n here. So it's 1213 to the power of 7, and then we take mod n, and that should give us this value here. On the other side, we take the G value and we raise it to the power of 16, then we take mod n again, and the value we get is this. Then Bob will send this value over to Alice. Alice will send this value. Then they do a calculation. So Bob gets the B value, raises it to the power of his X value, and Alice does the same, takes this value, raises it to the power of her value, and takes mod n. And at the end of it, they should hopefully end up with the same key. So we can see that this has actually worked. So just to prove that it will work again, let's try some new values. These are much bigger this time, and it still works. If you want, there are some test values that you can try, and we have some references that allow you to look to check that these values are correct. So here's an example here. And we can see here we end up with the same value. The code that we have, we use big integers because we can't really use the normal integers because they're normally only 32 or 64 bits. We need to use big integers to be able to calculate. We can see the calculation we get with G and N are prime numbers. We need to make sure they're prime. So we generate a couple of prime numbers, we get some big integers, and hopefully at the end our keys will match. And if you want to look at what the values really look like, if we were to use it in real life, that is a G value and that's an N. You can see how large these are. And then Bob and Alice generate a couple of numbers. And then the values that we get for A and B are these ones. And then hopefully when we calculate it on the other end, you can see here that the values are the same. So these become the keys that are used to be able to encrypt and decrypt. Okay, so again we've used big integers to be able to calculate, but it's the same type of formula, but we've just used a bigger value of G and N. Okay, so that just shows an example there, very simple example of how we can calculate this. There's the random value. We take 5 and 7, both are prime numbers, and this is our calculation. Unfortunately, Diffie-Hellman method suffers from the man in the middle, or the meat in the middle, where Bob thinks he's communicating with Alice, but negotiates a key with Eve. Eve, on the other end, negotiates a key with Alice, so that when Bob is encrypting, he encrypts with the first key, Eve then decrypts, then re-encrypts with key 2 and sends it back. Same happens the other way. Alice encrypts with key 2, Eve decrypts it, then re-encrypts. And as far as Bob and Alice know, they're actually communicating with each other, but actually there is 2 keys being used. The problem of passing keys was actually solved by public key encryption. In this method we can create 2 keys. One is a public key, the other is a private key. So if we send to Alice, we'll use her public key and she decrypts with her private key. In this way, if someone discovers a private key, we can just create two new keys and redistribute them. And the basis of the RSA method, which is one of the most popular public key methods, is the factorization of prime numbers. So here are two prime numbers, and when we subtract one and then from each and then multiply them, we end up with a value such as this. This type of number is actually quite challenging for a computer to be able to find the two values which actually made, or the two prime numbers which actually made that multiplication. So this is the challenge for computers. It's that they face with inside RSA. And it allowed us to get round the problem of creating a shared key. And it was Ron Rivest, Aldi Shamir and Len Alderman who created the RSA algorithm for public key encryption. And this is the basic approach that we have. So Bob and Alice both have public and private keys. So when Bob wants to send to Alice, he will get her public key, will then encrypt it, and then send it over, and then Alice will use her private key to be able to decrypt it. Another specialty of the public key encryption method is that we can actually sign something with our own private key. In this way we can identify ourselves and also that the message hasn't been tampered. If we take something in the message and then encrypt it, then with our private key, then on the other side they will then take our public key to be able to check that that message has been sent correctly. Only us with the private key is able to correctly sign something that the public key can actually verify. Okay, so this is the basic mechanism that we have. We have a message, we take Alice's public key, we then encrypt it, then we can't even decrypt it here at all, and only Alice's private key can then decrypt it. And so how do we distribute our keys? Well, one method is to use a certificate. So in this case, if Bob wants to identify himself, or if Alice wants to send Bob an encrypted message, she needs to get his public key. So the certificate is then sent over or is stored in a repository. The certificate contains Bob's public key. She then pops it off. She could put it on a keyring if she wants on her system, and then is able to use that public key to be able to send Bob a message. The authenticity of the certificate is very important, and it's the issuer that's probably the most important part of that. If Alice trusts the issuer, then she will trust it to prove that it is Bob's key. So how does Bob prove his identity? Now here we go. We take the message, and there is a special one-way function which creates a hash of the message, creates a unique code for it. So let's say we create MD5. So that will relate exactly to the message that was created. Then we'll take Bob's private key and we'll encrypt this MD5 and add it onto the message. As we'll see, it is this private key which identifies Bob. So next, as we're sending it to Alice, we'll take Alice's public key, and then we'll encrypt the whole of the contents of this message into there. So only key now that can decrypt that is going to be Alice's private key. So Alice then unencrypts the message plus this MD5, encrypted MD5, She then gets Bob's public key, which is distributed typically by a digital certificate, which she trusts. She is then able to decrypt the MD5. She does a check of the MD5 of the message, and then, if the two are the same, then she knows it was Bob who sent the message. Also, she knows that the message hasn't been changed on the way, so it adds a validity to the message that has been sent. So in this way, we can use public key to identify individuals, to verify the message, and also to keep it secret. So we've seen the importance of digital certificates to be able to identify users, to be able to sign for identities and so on. So one of the most important parts of this is the public key infrastructure, or PKI. With this, we can create repositories in which we can deposit our public keys in a trusted infrastructure. As the certificate itself contains some key information, such as the basic details for the certificate. We can then look at some of the properties of it. In this case, we can see the public key is RSA 2004 bits. We can look at the thumbprint for the certificate. This will define that it hasn't been changed. And a key part is obviously the issuer of the certificate. And it's this that allows us to define the trust level on it. The two types of certificates that we can have is either one with the public key, or we can have one that contains both the public and the private key. And we can see here that this defines a certificate that has both. So when we purchase a certificate, this is typically what we get, but when we export, we only export the certificate with the public key on it. It is often a good idea to back up any certificates that have both the public and the private keys on them. The formats that we have is we typically receive it in a P7B format. This is the base64 format. It starts with begin certificate and end. We can then import that. If we go to on Windows, Control Panel, Internet, Properties, and Certificates, we can then import our certificate that we have here. And then once it's in, it will be into our trusted certificates on our computer. So in this case, we can see here that we have a public key and a private key. So the basic formats that we have, P7B is a text format, P12 is binary, and SST is also binary. Okay, so this is what would happen, as we've seen before. There's the message. Alice sends over her certificate. Bob will then take the public key from there, encrypt, and send it over. Alice takes the private key from her certificate and then is able to decrypt the message. And on the other side, when we're identifying ourselves, Bob will take his certificate, take the private key off, then hash the value, add it to the message, encrypt it, then we'll send over his certificate. Alice then checks that, takes the public key off, and then is able to decrypt the hash. If she trusts this certificate, especially the issuer, then she trusts the key that's contained in it. A key part of digital certificates is to be able to prove the identity of an object or of a person. So we need some way for Bob to identify himself to Alice. In this case, we need something in between to be able to create a trust level. In this case, we bring in Trent. It is Trent that Bob and Alice both trust to prove the identity or provide the identity of each of them. Okay, so just to recap, what we have is we have some hashed message. It's then encrypted with Bob's private key. We send it over. Alice uses her public key to decrypt, her private key to decrypt. And then at the end of it, if the two hash signatures compare the same, then we've proven Bob's identity. A smart method that was created some time ago is PGP encryption. And PGP encryption gets around the problem of having to encrypt with public key encryption, because that can be quite intensive on the machine. So how it's created is that Bob will sign with his private key as before to create a signature, and then again we can then add that to the information. We'll zip it up. Then what happens is that we create a session key which then encrypts the message, and that provides us with our cipher. Then what happens is that we take the session key and then we just encrypt the session key with Alice's public key and then add the key onto the message. In this way we have used private key to be able to encrypt, but we use public key to be able to find out what the key is, or the session key for the mail. So on the other side, when we get the message back, the first thing that Alice will do is to be able to take the key. She then decrypts it with her private key. This will then give her the session key. She then decrypts the session key, and then so on as before, and then she proves the identity of Bob because he signed it with his private key. So before we finish with digital certificates, let's actually have a look at creating one. So in this case, we'll just create one, create a subject, give it a serial number, and it'll be valid for 100 days. So we'll get it to create for us. We're using Open SSL library here, and then that creates a public key for us. Here is a private key. That's what our private key looks like. And then if we wanted, this is what our certificate would look like. And we could obviously paste that in. If we want to have a look at what that creates, here is our certificate that we've created. Okay, so there's my issuer, there's the public key that we've created. There's the serial number we created, there's the issuer, and so on. We can see this is a self-signed certificate, so it doesn't have a path for it, so we shouldn't really trust this type of certificate at all. If we wanted, we could install the certificate, and this would install it onto our machine. We can see that it's valid for 100 days. Okay, so if you're interested, the code should also be provided. Let's have look at a few other certificates. Okay, so in this first example, we just load it up. We can see this is a self-signed certificate. This one here is also self-signed. We can have a look at it if we want by clicking here. This one here is issued by Cisco. Let's have a look at that one. In fact, this is a Google certificate. And it shows us the details of the certificate, including the issuer. And Google have issued that one. Let's have a look at this one. And this one is Cisco. Okay, so we can see the certification path is there right up to VeriSign. We can see all the basic details of the file, such as its subject, its validity, who issued it, and so on. And we can see here that this is trusted for certain things like proving the identity of a remote computer. This one here is Microsoft. And again, a key thing is the certification path that we can see that takes it right up to VeriSign there. It has the issuer, the public key, quite a big public key in this case. Okay, so now let's look at another encryption method and also a method that can be used to sign, and that's LGAMO. So with LGAMO, the algorithm is that Bob pricks a prime number P and G, and the value of G is somewhere between 1 and P minus 1. He then selects a value of X, and that's going to be his random key. Next, he picks Y, and then he sends G, P, and Y to Alice. Okay, so Alice receives G, P, and Y, takes the message, creates a random number K, and then calculates A, which is the G value to the power of K, and then we take the mod of P, and then she calculates B, which is Y, the Y value to the power of K, and then takes the message and takes mod P. She then sends the value of A and B to Bob. Okay, so let's see this in action. Okay, so let's calculate a P and a G value. So then Bob selects a random value, which is X, and then he calculates Y, which is G to the power of his X value, a bit like Diffie-Hellman, and then takes mod P. So it's 2461 to the power of 165, and then takes the modulus of P. So we end up with the Y value. Bob sends over G, which is here. He sends P, and then sends the Y value. So this is his private key here. So then Alice creates a message. So in this case we'll make it 131. She then takes a random value. We'll take 128. Then calculates A. So A is going to be the G value to the power of a random value, and then mod P. P is one of the values that's been sent over by Bob, and then takes the B value, which is the Y value that was sent over here, raises that to the power of her random 1k, multiplies by the message, and then takes a mod P, which was also sent over from Bob. Then the A and the B value are sent over, and then Bob takes B divided by A to the power of X, and then takes mod P, and ends up, hopefully, with the same value as Alice had in her message. Let's try another one just to see if it works. 129, we've got 170, and it works again. So Elgamal allows for smaller keys than RSA. It's important that we use prime numbers for P. G just has to be a value between 1 and P minus 1. So up to now we've used two main methods of encryption. One is using symmetric encryption. We use the same key to encrypt as to decrypt. Then we use something like Diffie-Hellman to be able to exchange the keys without Eve finding them out. We looked at asymmetric encryption, such as with RSA, where we have a private key and a public key. If we send to Alice, we use her public key, then she can decrypt with her private key. We can also use it for identity, where Bob signs something with his private key, sends it over, and she uses his public key to identify that it was him that sent the message. The third method of encryption is known as one-way hashing, where it shouldn't be possible to go back the way mathematically once we hash or create a signature of something. So it's typically used to identify a standard signature for data. One of the most popular algorithms is called MD5, and it produces a 128-bit signature. In hexadecimal, each character is 4 bits, so we have 32 characters defining our hexadecimal base MD5 signature. We can see if we change just one letter, then it completely changes the hash signature, and it doesn't matter the length of the data, we always produce the same size of signature. We can also produce a base 64 version of it, such as this one. So let's have a look at an example. Okay, so let's find MD5 in SHA-1. SHA-256 gives us 256-bit signature. SHA-384 gives us 384 bits. SHA-512 gives us 512 bits. Okay, so we can put in a hash signature. If you want, we can also put in a hexadecimal value, such as DDCA. I'll take the data for that, but normally we would put it in as text. We can take some tests if we want. And you can see, there we go, that gives us our basic test vector here for that. Okay, so there's a whole lot of test vectors for that. And we see hash values extensively within passwords, such as for MD4. We can create a hash value for that. We also see it within inside Cisco routers for the hashed value of the password. Unfortunately, it can be cracked fairly easily because the intruder can build up a dictionary of words, well-known words, and then use a rainbow table, which is the hashed values of each of these words, and then looks up the rainbow table till it finds a match. And when it finds a match, then that relates to the value that it's been hashed with. Okay, so let's have a look at an example of this. Okay, so these are some pre-prepared hash values. We'll see how quickly it takes to find those ones because it's been pre-prepared. So let's, as a test, let's go and find a site, and we'll take the fifth word. Okay, it's 1, 2, 3, 4, 5. We'll take this word here. And then what we'll do is that we'll hash that. We'll come back here and see if we can crack that. Okay, so there's MD5, so we'll go back to our program again. Put a hash, so let's hope that's going to work. And you can see there it takes just a few seconds to be able to find the reverse of that. And this is because in the cloud we can get a massive rainbow table, terabytes of data of well-known words that have been hashed. So you can see these are some examples here for Washington. If we try that, it just takes a second or two to be able to get that back again. Okay, so hash signatures are very weak in terms of the rainbow tables. The other thing that we can have with a hash is that we can get a collision where the different data produces the same hash signature. Normally it would be very difficult to get the same context between the data that produced it, but we can get one that can have a similar context and even ones that can have a full context. And it's been shown that it doesn't take a lot to actually produce a collision. 2 to the power of 64 is all it actually takes to have a better than 50% chance of creating a collision. And with SHA-1 it's been shown that it can take up to 18 hours to find a collision. So let's look at an example. So we'll have a look at MD5 again, and we'll just pinpoint an example of a collision. Okay, so here's one here. So we've got some data, and we're going to change this one to an F, this one here to a 2, and so on. So when we try this, we should get this as a hash signature. Okay, 7905, 7905. Okay, so now we'll try the other one. And we get the same hash signature. Okay, so we've taken the hexadecimal input there, and you can see here that the two values differ by 1, 2, 3, 4, 5, 6 different hex values, and it still produces the same hash signature. Okay, so this is known as a collision. So what we normally do to get around the problem of rainbow tables is that we create hash signatures which vary either over time or each time we produce a new password. So a good example of that is with bcrypt. So with bcrypt, every time we produce a new password, it will produce a new one for us. This part here identifies that we're actually using some salt as part of this. We can also use OpenSSL, and we can create our own salt value. So if we do ABC here and encrypt and BCA, you see we produce different values. If we want it to use its own salt, then you can see every single time we create a new password. This is for a standard Unix password. It will create a new password for us. So let's look at a weak hash. Hash methods MD2 and MD4, they were used before MD5 came along and have now been compromised. Okay, so it just works in a similar way to MD5. And we can try some tests. So in this case, what we have is that we have two hex values here as an input data. And you can see this varies from that. And we have a different value over here too. So when we feed this in, it should produce this as an MD4 signature, and it does 4D7. And then when we feed in we just check the value that goes in. There's the EDD there, EDD. And now if we try this one, this should have EDC. And you can see that it produces the exact same hash signature. So we found a collision for our data. And this is another one that you can try that should produce the same MD4 hash. Another well-known hash signature is the LM hash. So this was used in Windows to be able to store data. So we can take a password and it produces our hash value. The one thing to notice is that this value actually always stays the same, which really doesn't help the strength of the actual hash. When the password is less than 8 characters. If we take a longer one, then we get a full sort of length of password for it, but it is very weak in terms of just having less than 8 characters. So if we try that, it should get much stronger after that. Okay, so some of the other methods that we can have MD5 with salt. Whirlpool is another hashing method. RIPIMS 160, Tiger, and the new one that's came along, it's known as KEKAK, and it's a new algorithm, and it's been defined so that just in case there is a problem with SHA-1 and SHA-2, then hopefully SHA-3 will not be compromised. Okay, so this is brand new, and it was in October 2012 that it won the NIST competition. So you can actually try some test vectors and hopefully you'll get the right result. You can go right up to 512 bits. So this is the test vector that we have here for it. So there's a growing increase in the usage of one-time passwords, where we register a password, and then each time that password will change. So it might be that we want access to some data, and then we register once, one-time password, and then each time our password will change. So it's very difficult for Eve to find out what the next password actually is, because she hasn't been part of the registration and part of the sequencing. So the ways that we can do this is to be able to have a function. It takes an initial password, then does the same method on that password again, and then does it again. So it could be MD5, so we could hash a password, then hash it again, and then keep hashing it. So only by knowing the original message could we actually determine what the next one is likely to be. Obviously it would have to know the function. We can have a timed password, where the password is only valid for a certain amount of time. So it could be between 1 hour and the next, the password is only valid there, and then for the next hour it's another password, and so on. Only by knowing the original seed could we actually determine what the next password was. Or we can have a counter, so that every time we access, we'll automatically create a new password. Okay, so let's have a look at timed and hashed one-time passwords. Okay, so in this algorithm what we're going to do is generate a new seed, and then each time we create a new one-time password. Every time that we click on the button there, it will create a new one. Only by knowing the original seed can we actually determine what the next password is going to be. Okay, and all it's doing is taking a function, then applying a new function onto it. We can also have a timed password. So in this case, we've defined a 5-second window. Okay, so it becomes valid. So even if we press it, it won't work. Got to wait 5 seconds, and then we can generate a new one. Wait 5 seconds. Generate a new one. We can generate a new seed. Then generate the one time. So we've got to wait 5 seconds, and so on. So this is a good method for changing it over time. And then we can have a counter based hash. So I can see that every time a counter changes, it'll give us a new one. If we try Bill, there we go. Okay, so this allows us to be able to time use a counter to generate our one-time passwords. So sometimes what we want to do is to be able to authenticate a message from Bob to Alice to make sure that the message is signed correctly. One method is known as HMAC. So with HMAC we take the message, we take a hash of it, but then we apply a secret key onto that hash. And then we send that over, and then only with the secret key can Alice determine the hash of the message. So if the hash HMAC messages match, then everything is correct, and the intruder hasn't got in and changed the message. So normally we create a session key. At the start of a session, we might do Diffie-Hellman and create a secret key. After that, we can use HMAC to authenticate the messages. So let's have a look at an example of this. Okay, so we've got a couple of one. There's Mac 3des, based on 3des, and this is HMAC. So we have Fred, and we'll have a key of Bert, and it produces these values for us. If we go for test 1, 2, 3, and hello, it produces this as a SHA-1, HMAC SHA-1, which is the same as our test there. So an example of this is the EAS CCM. CCM, what we have is we have some plain text, we apply a key, and we apply an IV. It will then generate a MAC for us and the cipher, and then the other end we can actually check the message with its MAC code. So this is known as AES counter with CBC MAC, and you should find that there's an example of this on the website here. And we'll take an IV of 1, and that will produce our message authentication here, or a MAC code, and when we decrypt it we can see we get the right value, and it's the MAC code that we can check to see that the message hasn't actually been changed. So let's have a look at a few other little things. We'll have a look at secure function evaluations and also in some advanced cryptography. So with normal public key encryption, what we have is we encrypt with one key, then we might encrypt with another key. So if this was Bob encrypts, and then Alice would encrypt, and then what must happen is that Alice must decrypt, and then Bob will decrypt. Okay, so it's a standard applying the encryption and then taking it off again in the right sequence. With cumulative encryption, what we have is that we can encrypt with Bob, we can encrypt with Alice, and then Bob can actually decrypt followed by Alice. So it's a smart way of actually defining that users can put a lock on the encryption, and then it can be unlocked one at a time in whatever sequence. So let's have a look at this as an example. And what it is it's a special example of RSA. Okay, so we go through the normal sequence of it. Okay, so there's our encrypt and decrypt, everything's working up to here. Now what happens is that Bob sends N, P and Q. So the values that Bob used here, N, P and Q are going to become the seeds of the encryption keys for Alice. So again, so there's the N value, there's the phi is calculated from the P and Q, so those values should be the same as what we had before, 15 and the 28. And now Alice takes an encryption key of 5 because it's between 1 and the 28 value. And now Alice can generate her key. Then finally, she gets her decryption key. And we can see here, there's the message. Bob encrypts. Alice encrypts. When Alice decrypts, we get a 48 value, and then when Bob decrypts, we get 32. If we take it the other way, 48, 50, and then Bob decrypts first, we get a value of 40, and then Alice decrypts, and then there we go, so 32. So this is known as cumulative encryption, a smart method of being able to use the different keys. It's not as strong as RSA because we're obviously giving away some of the parameters, but it's a good method for some specialist applications. And another method that we have is called secure function evaluation. In this way, what we're going to do is that we're going to determine the total votes counted without Alice, Bob and Carol actually revealing what the votes are. So Bob calculates 3 values so that the vote, his vote, they equal his vote plus 100. So we want this to be 102, which it is. Alice then creates 3 values. She wants her value to be 101. So she takes those 3 values. Carol then does the same. Carol has only got 1 vote, so that should total 101, which it does. And then Bob gives Alice his second value. Carol gives Bob gets Alice's second value, Carol's second value, and then adds it to his own. So this is the 11, the 14, and the 1. Alice gets Bob's second value, Carol's third value, and adds it to her own. She gets 170, and then so on. At the end of this, we add them all up, and then we take modulo 100, and we end up with 4, which should be the same as the original votes that's actually cast. We'll try another one to see if we can get some more votes this time. This time the number of votes is 19, and there we go. Try another one, and we end up with 21, which is correct. And this is known as secure function evaluation. A last little method that we have is called Shamir's secret sharing. And with this method, Shamir was one of the people who invented RSA. We can have a secret message, and then we can define a number of shares. So let's say we have 5 shares. We have 5 directors in a company. And then what we want to do is that any 3 of the directors can put their shares together and actually create the secret message back again. Okay, so when we run it, it creates 5 shares for us. And then when we take any 3 of these shares, it brings the message back again. Okay, so in this way we can actually define how the data split, and then how many things are allowed to bring it back together again. Okay, so that's been an overview of some advanced cryptography.